So after this small experiment about shielding, we can have a look at the exercise task. And I would suggest to have a look at this exercise task 16, which is about shielding. And so we have a single metallic wall. We should calculate shielding efficiency according to our Schelkunoff theory. And the material of the wall is at first some aluminum. The conductivity of aluminum is given here, and the thickness is also given, 50 micrometers, and then it's already written here, this is aluminum foil, like aluminum foil that you could buy also in many department stores. And so now we have several tasks to calculate what is the shielding efficiency of this foil in the near field, in the far field, against some electric field, near field, magnetic near field, and so on and so on. Okay, so what I will do is at first I will copy this here to my drawing program, and then maybe go back to the browser, go back to our course here, and also open up the lecture slides. That should be also available somewhere on the internet, and go to the chapter about shielding. Which is here because we might need to have the formulas related to this. And so here was this shielding theory explained that has been developed by this guy here, Schelkunoff. And so here we have all the corresponding formulas. And so now I will maybe also go to full screen here and set this to page size. And scroll forward until we have the formula, right? And here we got the formula for the shielding attenuation. The very general one that included these two transmission coefficients, propagation constant, reflection coefficient, and one more term here for the propagation. This was, let's say, our reflection loss, this was absorption loss, and this is this correction term due to multiple reflections. And so, as we also have Octave here available, we could also do this calculation, and we could of course also compare it with these simplified formulas that we derived here, for example, for this far field calculation. So that's probably what we are trying to do. So let's start, try to start with task A. How large is the overall attenuation due to reflection, absorption, and this discussed multiple reflections if we have a far field source, a distant source, and we have a frequency of 100 megahertz. And yeah, so maybe we start with this simplified formula here. So I will copy this and paste it into the drawing program. And so for task A, we can just calculate this. And the question is, so our frequency in megahertz would then of course just be 100. The mu relative of copper, of aluminum, is aluminum some ferromagnetic material?
So permittivity, aluminum is...
Yeah, so now we are talking about here about this mu, about permeability.
Yeah.
And so aluminum is not a ferromagnetic material. So the relative permeability
will be high.
No, will be just 1.
Oh.
It's just the permeability of aluminum is just free space vacuum permeability, no relative permeability. And the kappa relative, as we discussed, is the conductivity of aluminum normalized or divided by the conductivity of copper. And so the copper conductivity is given here on the slides. This is 57 times 10 to the power of 6 Siemens per meter, and for aluminum we have 35. So if I already go to Octave, maybe make this window a little smaller, and this always fails, so I have to go back to the standard settings. Okay, so we can say our kappa relative, or maybe if I insert the values correctly, kappa of copper is 57 times 10 to the power of 6 Siemens per meter. The conductivity of aluminum is 35 times 10 to the power of 6, and the kappa relative is the kappa of aluminum divided by the kappa of copper. And so we should get something like 60% or 0.614. Okay. I will note this down here, 0.614. And so then we can insert all this stuff into our equation, and maybe it would be a good and better idea if, because we want to rerun this several times, if I do not do all stuff on the command queue, but open up some script in my editor, maybe say at the beginning clear all. And so then in, let's say, task A, or maybe this also already belongs here to task A, we can say the reflection loss is 108 minus 10 times decadic logarithm, which is log 10, and then mu relative multiplied with the frequency in megahertz and divided by kappa relative. And with a semicolon I can escape or suppress the output here. And of course for this calculation we need to have the values of mu relative, which is 1, and the frequency in megahertz is just 100. And so we should get a value. So if I save this and maybe say it's task 16, why does it not work? I'm in the right folder and it's saved under task 16, and if I run it, it says it's undefined. Why is this happening? Okay, let's start Octave once again. Did this happen to you before?
Sometimes clear all problems, I don't know why.
Sometimes clear all makes problems, okay. And now it's working. For a strange reason, now it's working. Okay, and we get 58 dB. So if I add this here, or let's, no, not 58, 85, or let's say 86. So here at the end we get, or maybe if I can try to move this a little bit to this side and I have more space, we get 86 decibels of shielding. And there's a question.
So for the exam, we have to also write in Octave or in MATLAB?
For the exam, you could do it because we do the exam in the examination in the online exam, or no, not online, in the electronic examination center at our IT department, Rechenzentrum. So I don't know if they have Octave installed, but they for sure have MATLAB installed.
Okay.
And so
is it mandatory?
And you can also use a calculator if you like. But of course in Octave it might be on MATLAB, it might be simpler to do the calculation.
So the Octave here are just only for the calculation, or for the to show how the because if you do the calculation we will only put the value.
Yeah, so if of course if you that's a good question. So from your notes or from whatever you submit, the formula should be visible, and then you can say, okay, you have done this and this calculation in Octave. But if you do the calculation in Octave or on your plain calculator, I mean, if you do the calculation on the calculator, I won't also see what you typed in into your calculator.
Yeah.
And maybe there will be some way where you can submit your Octave commands, let's say.
So
That you
actually, is it mandatory to submit the Octave command?
No, it probably won't be mandatory. It will be optional.
Okay, so just we will write the formula and we will put the values, and if we find the result, it's okay.
Exactly.
Yeah. Okay.
Yeah, it's imagine like Octave is something like a powerful calculator. If you do the calculation on your plain calculator.
But it will take time for the exam.
But I think that in this case, for example, you have also to write how do you calculate k relative, I think.
Yes.
Yeah, and so I would say if you write it something like this, it should be sufficient in this way, how I have written it down here.
Okay.
Okay, so we have used this approximation formula, and as we have Octave now, we could go back to our general formula, the one that was given here, and also try to use this formula in this case. So I will maybe also copy this, just put it into the drawing program, and maybe a little smaller that it fits here. And go back to the editor. And so now we could also calculate this general shielding efficiency, and this is 20 times decadic logarithm log 10 of the absolute value, right, of 1 divided by the transmission coefficient from air into metal divided by the transmission coefficient from metal into air. This multiplied with some exponential function of gamma times the thickness, and multiplied with this term 1 minus the reflection coefficient from metal into air, this squared, multiplied with another exponential function of minus 2 times gamma times t. And times t, good point. And so this closes this parenthesis, and I think this closes the absolute value, and this closes the decadic logarithm, and the last one would be wrong. Okay, so now we have the exact formula. Maybe before we go to the exact formula, maybe a good point would be this is just the reflection loss. I mean, if we go back to the formula, our total absorption is not only reflection, it's reflection plus absorption plus this correction term for multiple reflections. So we should also have a look at this absorption term maybe first. So I will scroll forward. This is the absorption term, and this is our numerical value equation here. So let's copy this, go back to the drawing program, and so here we need to insert the thickness and all the other values we already have. So how do we get thickness in millimeter? Or what would be the value if the real thickness is 15 micrometer? If we convert this into millimeter?
So we have to multiply by 10 to the power.
Yeah, but 10 to of which power do we have to multiply?
It's already minus 6.
Micro is 10 to the power minus 6, milli is 10 to the power minus 3. So if we want to count, then it will be 10 to the power minus 9. 15 into 10 to the power minus 9.
No.
It's 0.00.
Micro to milli,
Yeah, it should be 0.015 millimeter. And so if we do it like you would have to have done it. So the real thickness is 15 micro, and micro is 10 to the power of minus 6. And so now if we want to have the thickness in millimeter, we take the thickness and multiply with the millimeter is 10 to the power of -3, so we have to multiply with 10 to the power of 3. And so if we do it like this and check, so I can execute this here, and so we get the 0.015. And this is what we insert into this formula. So our absorption loss is 130.3 dB times the thickness in millimeter that we just used, multiplied with the square root of the frequency in megahertz, multiplied with the relative permeability, multiplied with the relative conductivity. And that should be it. And so if I execute this, F9, go to the command prompt, we get another 15.3 dB. So this is, oops, not this one is 15.3 decibels. And so the 15 is larger than 10, and therefore if the absorption loss is larger than 10 dB, we don't need to take into account the multiple reflections. So our total shielding efficiency is R plus A, and in our case, so if we say AS is R plus A should be 100 something. Should be roughly a little more than 100 dB.
You didn't take the A.
I forgot to take the A here. F9. So 101.2 dB. 101.2 decibels. And this is now the same thing that we should also get if we take the more exact formula here. And so for this more exact formula, as we have seen, we need to have the transmission coefficients, TAM, TMA. We need to have gamma, the propagation constant, and we need to have this reflection coefficient from metal into air. And there's a question.
A is the 130 dB, right? 130.3 dB.
A 15.30 absorption loss.
The capital A is 15.3.
Ah, okay.
Yeah, and so this and this together gives this value.
Okay.
And this is the total shielding efficiency or total shielding attenuation. Okay, so let's go back to this formula here, which was on this side. And yeah, I mean, interestingly, I think there is some typo here that no one really ever noticed. No, it's not a typo. So the minus from here, because we have 1 over this turned into a plus. That's why we have the plus here, but it's still the minus here because this is still like this from the denominator turned into the numerator. Okay, so it's a plus here, but it's a minus there. I can check back in my formula. It's a plus here and it's a minus here at the end. Okay, so now we need to have formulas as set for the transmission coefficients, for the reflection coefficients. So we can go back here a bit and check these. Here are the transmission coefficients. So the transmission coefficient from air into metal, this one here is 2 times the characteristic impedance in metal divided by the characteristic impedance in metal plus the characteristic impedance in air. The second value here is 2 times ZA, and everything else is okay. So to have this, we need to, of course, calculate wave impedance in metal, wave impedance in air. We need as a value. And there should be also the reflection coefficient here somewhere close. This is the reflection coefficient from metal into air. So this is also ZA minus Zm divided by the same sum that I can copy from here. Okay, so we need to have wave impedance in metal, wave impedance in air. And this was also given here somewhere on the slides. This is the wave impedance in metal. So the wave impedance in metal, I will use this approximative formula there, is 1 plus J divided by kappa and divided by delta. And so for the kappa, I need, of course, to use the kappa of our aluminum. And, okay, we need to calculate delta. And delta is the skin depth. This is given here. It's 1 divided by the square root of P multiplied with mu. I will call this mu aluminum, multiplied with the kappa of aluminum and multiplied with the frequency. And so I'm not sure if we have yet used the frequency. We just have frequency in megahertz, so I will write the real frequency, which is 100 E6, and from the 100 E6 we could take the frequency and divide by mega, so we get just 100. Okay, then we need to have the real mu, and so for this we should use mu 0, the permeability in free space, and this is
8.8.
no 8.8 for this was epsilon, this was permittivity.
Yeah, but mu naught is the.
It's the 4 times P times 10 to the power of minus 7, and the unit is
by 10 to the minus 7
volt second divided by ampere meter. And so then the mu of aluminum is mu 0 multiplied with the mu relative, so in this case it's just mu 0. Okay, so we should have all values here, P, mu, kappa, frequency. Then we can calculate this wave impedance in metal. And we still need to have the wave impedance in air. This was also given you on the slides for a far field source. It's the 377. Yeah, so we could also calculate this from epsilon 0. Epsilon 0 is, as you just said, 8.854 times 10 to the power of minus 12. And so our wave impedance in air should be square root of mu divided by epsilon, right? Mu 0 divided by epsilon 0. And so if I run this once again until here, F9, so we should get that wave impedance in air is approximately the 377 ohms. Okay. So then the last thing that is missing is gamma, is the propagation constant. But this was also somewhere given on our slides. I'm not sure about the right direction, no, probably somewhere forward. When we discussed the absorption loss here. So this is gamma. And then we had this approximation that it's 1 plus j also, and this is 1 over delta. So if we have 1 plus j divided by delta, yeah, that should be it. So our gamma is also 1 plus j divided by delta. And so it's somehow the same formula as here, but this also includes conductivity, and this just includes this delta term. Okay, so now we have all stuff just let's run it again, and so this was the result here. Yeah, and okay, so maybe leave it like this and call this exact. And maybe don't escape the output here. And so from the approximated formula we get 101.2 decibel. From the more exact formula without so many approximations we get 101.5. Okay, almost no difference. Fits very, very well. Okay, excellent. So then we can continue with task B. For this I will use green, and in task B we leave everything constant. The only thing that we change is we change the frequency to 2.4 gigahertz. So in task B now F is 2.4 gigahertz. So this means our frequency in megahertz then will be
megahertz. Giga is 9, so it will be multiplied by 0.2.
Yeah, so how if we have a frequency of 2.4 gigahertz, which is as said here, Wi-Fi transmitter, microwave oven, Bluetooth, how many megahertz will it be?
It will be 2.4.
Yeah,
2.4.
It's 2,400.
400.
Okay. Yeah, and so now we need to insert this back. Well, maybe I should go back to this here. Yeah. So now we need to change the value here, and we need to change the value there. And we could say, okay, so if we have a larger frequency here, this term is getting larger, so our reflection loss should get smaller. But if this frequency here is getting larger, then the attenuation should get larger. So this is getting larger, and probably this is getting larger, then this is getting smaller. So our overall attenuation should increase, hopefully. Okay, so we can do it again. I think I have some space here to write. So we need to recalculate R, we need to recalculate A, and we need to recalculate our total shielding efficiency. And yeah, so now I have the big advantage that I have Octave here, and I need to just need to change some values in my calculation. So I will enlarge this a bit and add a new section here for subtask B. And in subtask B, as discussed, our frequency is 2.4 giga, which is 10 to the power of 9. And I can do the same calculation for the frequency in megahertz, divide by 10 to the power of 6. And so kappa will stay the same, epsilon and mu will stay the same, but starting from here, the thickness will stay the same, but we need to recalculate the reflection loss. We need to recalculate the absorption loss. We need to recalculate the total shielding efficiency for sure. And so if the frequency changes, delta will change, all these parameters here will change, so I will also just copy this. And then maybe escape all the output here on the top so that we don't see this anymore. So we should now only see values from the new calculation. This one here also needs to be escaped. And okay, let's run. There's no error, fortunately, in the script. So the reflection loss, as discussed, this was going down, decreased to 72 decibels. But the absorption loss increased, as already discussed before, to 75. So 72, 75 together is 147 decibels of total shielding attenuation, and this is once again much larger than 10, so we don't need to take into account the multiple reflection loss. And if we do the exact calculation, the agreement is even better, and so this exact formula also works very well here, or let's say better to say the approximation in this case works.
A75, where did you find this?
The A I got from, or we got from this formula here.
Okay.
And so this is the same value as before, this is the same value as before. We increased the factor from 100 to 240. So it's some increase by a factor of 24. And the square root of 24, right, the square root of 25 would be 5. So the square root of 24 is a little less than 5. So we take this and multiply by 5, by a little less than 5. And so 15 multiplied with 5 is 75. Perfectly makes sense, I would say.
Yeah, exactly.
Okay, then let's continue with task C. How large is the overall attenuation for a high impedance field? For a high impedance field now at the frequency of only 4 kilohertz. So, for example, we have some frequency inverter of some variable speed drive, of some motor drive system, and the distance between the wall and the source of the field is this 0.35 meter. And so I think I don't have too much space here on this slide, so I will go to the next one. And so for task C, now we are in some high impedance near field, in the near field of some electric dipole. So we need to go back to our slides and check and remember that there was some approximation, this one here for the high impedance field. This is the numerical value equation for the high impedance field. So let's take this equation and go back to the drawing program, paste it here, maybe make it a bit smaller. Okay, so we still have the same mu relative. We have a new frequency. So the frequency in megahertz now is, if we convert 4 kilohertz into megahertz, no, not 400.
No, it will be divided by 10 to the power 6. So 4 kilohertz divided by 10 to the power 6. 4.
Yeah. So what do I need to write? So the result is.
Wait.
Interestingly, I would not need the calculator, or I would not. I mean, it's. This is definitely some skill that you should improve.
Yeah, 1 divided by 10, so it will be 0.0.
Yeah, 0.004.
4, yeah.
Exactly, and so this source distance in meter is already given in meter. So Rm is 0.35 without the unit meter, right? This is just a number. Because otherwise this equation here would not fit in terms of the units. So now in task C we can insert all this stuff into this equation. So I will add a new section here for task C and maybe also escape all the output that we had here from the task before. And so in task C, our frequency is 4 kilohertz. Kilo is 10 to the power of 3, right? If we do the conversion into megahertz, it's like this. And so we need to have a new formula for the reflection coefficient, this one here, which is 42. minus 10 times decadic logarithm of mu relative multiplied with the frequency in megahertz now to the power of 3 multiplied with this source distance that we need to give to the power of 2 and divided by relative conductivity. And that should be it. And the source distance is 0.35. And okay, maybe not, let's not escape the output here. So we see the value and it's 220. And this somehow makes sense, or 221 decibel. And this somehow makes sense because if we go to some high impedance field impedance will be higher than a 377. So inside our formula, for the reflection coefficient, this one here, the difference will be larger. And so the reflection coefficient is closer to 1 and we have more reflection, and that's why we also have more reflection loss. Okay, so then I can just copy the formula for the absorption loss, and I can copy also the formula for the total shielding attenuation. And calculate this. So absorption loss now is very, very small because the frequency is small, so the skin depth is getting large. So now as this A is smaller than 10 dB, now we need to take into account this term for multiple reflections. Still, we can use this approximation here and say our wave impedance in air is much larger than the wave impedance in metal because we have this high impedance field. So this simplification here should be okay. Yeah, so let's take this M, copy it here. So I can note that A is more or less 0 dB. So we need to calculate this M. This is a bit of a challenge with the usual calculator because you need to have this complex exponential function, and you maybe, if your calculator cannot do it, we need to break it down into sine and cosine and so on. Absolute value should not be a problem, and decadic logarithm of this also not. So here we can have it simple. We can say that M is 20 times decadic logarithm of the absolute value of 1 minus exponential function minus 2 times gamma times the thickness. So closing parenthesis, that should be it. And so now we need R plus A plus M. And I will run it. And this cannot be, M cannot be that small. Something must be wrong in my formula here. 1 minus. Yeah, probably I need to recalculate, of course, gamma first. Gamma still has the old value. So we need to have delta at first, and from delta we can calculate gamma. And yeah, now it fits. Right now we get something negative that decreases our shielding attenuation. So M is minus 30, and the total shielding attenuation then, if I write this down, AS is R plus A plus M, is approximately 191 dB, so still quite a lot. Okay, and we could check if our exact formula also gives us this result. So we need to recalculate wave impedance in metal, and we need to have a new formula for the wave impedance in air. And so for wave impedance in air, now we need to take this formula for the near field, which was given somewhere here. So we have the high impedance field of the electric dipole. Right, maybe I will copy this. Paste it somewhere here. So now we need to have this formula. And the term that we have, square root of mu divided by epsilon, this is the Z0. So now we need to multiply this with R0 divided by the source distance R. And okay, there I can use also Rm because it's in meter. Yeah, and we could also take into account the minus J term, but I think at the end this might not make a huge difference. So we need to calculate R0, this transition distance. This is also given on the slides. This is this here, lambda divided by 2p. Okay, and this is lambda divided by 2 and p. And how do we get lambda?
C by F.
Lambda is c divided by f. So the frequency we don't have c yet. And c is what we could calculate here in general. Because how does c, or maybe I will call it c naught. How does c depend on permeability and permittivity?
C is the force of the light, right?
It's velocity of light.
Velocity of light. So in the open air space?
In vacuum.
Yeah.
Or in air, in the air space, in the air medium.
In the airspace, the velocity. You mean if the frequency?
Yeah. How can I calculate c from epsilon in mu?
Okay.
And so we can check the unit of epsilon, as discussed, is
Epsilon equal to
is ampere second divided by voltmeter. And the unit of mu is?
Mu is, there is no...
Is volt second per ampere meter.
Okay, for the air there is no...
And for the air the relative permeability is 1, but the absolute permeability still has this value, and has this unit. So what would we need to do with mu and epsilon at the end? And what is the unit of the velocity? Meter per second. So what would we need to do with mu and epsilon to get meter per second at the end?
Okay, so
Mu by
Yeah, if we have mu multiplied with epsilon, then ampere and volt would cancel each other, but we get seconds per meter. We get seconds squared per meter squared. So we need the product of the two, then the square root, and then the reciprocal value. So if we calculate c as 1 over the square root of epsilon 0 multiplied with mu 0, then it should be, what is the value of velocity of light? 3 times 10 to the power of 8. And if I just execute this, we get 3 times 10 to the power of 8. So this fits. Okay, so from this we can calculate lambda here. From this we can calculate wave impedance in air. And so then we can recalculate the transmission coefficients. Oops. Gamma we have already. We can recalculate the reflection coefficient, and we can recalculate this total shielding efficiency. And if we have done everything correct, what I hope, then we get also the very same value there from our exact formula. So this also fits very well. Excellent. Then we can continue, and for this I will take red. For subtask D, how large is the overall attenuation for a low impedance field at the same frequency and with the same source distance, but now it's not an electric dipole that we assume as a source, it's a magnetic dipole. So we have a low impedance field. So in task D, we need to take the formula. This was high impedance field, this is the low impedance field. And here we got this formula. So I think we already have all the values. We just need to reinsert them and calculate this value. And this is what I will once again do in Octave. So yeah, we have finished this subtask, so I can escape the output here. And we continue with D. And for D, the reflection loss is 74.5 minus, once again, 10 times decadic logarithm of mu relative divided by the frequency in megahertz divided by the kappa relative and divided by the source distance, once again squared. And so this should be our reflection loss. If we check the formula for the absorption loss, nothing should change. If we check the formula for this multiple reflections, also nothing should change. I should maybe add the minus 30, the unit dB here, even if it's just a pseudo unit. Okay, so absorption should be the same, multiple reflections should be the same. So total shielding efficiency can be recalculated, and yeah, so let's do this. So now we have much less reflection because wave impedance in the air is much smaller. So if we check the formula for this reflection coefficient, now this is small, this is also small. Now the difference is not that large anymore, and so that's why the reflection coefficient is much smaller. So yeah, we only have this 40 dB of reflection, but we lose also 30 dB due to this multiple reflections. So our overall shielding efficiency in this case is just 9 dB, which is not that good anymore. So this is 39 dB. No, maybe I should switch to red. 39 dB. And so our overall shielding efficiency is just 9 dB, which is not that good. Okay, here we can also try to recalculate the exact way. So we need to have a new formula for the wave impedance in air. And if I go back to the corresponding page on the slide, which should be somewhere here, for the magnetic dipole for the low impedance field, we have this formula. So here is the reciprocal value, and the minus j turns into a plus j. So I can change this at the formula, minus j into plus j, and then it's source distance divided by the transition distance. Nothing else changes, so I think we just need to recalculate everything that follows here. The transmission and reflection coefficients and the new formula for the exact impedance. And I might show the result here, not escape it. And then once again, the exact calculation fits quite well to what we did with the approximative formulas. Very good. We are good in time. So we can continue. And for this, I will once again use blue with subtask E. How large would the overall attenuation be in the same conditions as in task D if now we use steel instead of aluminum? And steel has some relative permeability. And so it will not help for the reflection, because higher reflection will make less absorption, but it might help if I go back to the formula here before, if we have more.
Here for kappa is for iron?
Yeah, and kappa is for iron, because iron and steel have the same conductivity, more or less. Yeah, more or less. I mean, iron and steel, okay. Don't do this discussion with mechanical engineers, but as an electrical engineer, I would say iron and steel is the same. From an electrical point of view, it's quite similar. From a mechanical engineering point of view, of course not.
Yeah, it's not different.
But from an electrical engineering point of view, it's more or less the same. But the relative permeability will help us here. So if we change from aluminum to steel, if we change here from aluminum to steel, steel has less conductivity, so this will decrease, but it has much more permeability. And so this might help us in getting more, more overall shielding efficiency. So I will once again copy the task sheet and paste it here to this page. And as said, take blue to continue with subtask E. So what we would need to recalculate is the relative conductivity of this steel or iron. So yeah, we take 9.3 divided by the 57 that we had from copper, and so we should get a new value. And mu relative is 300. And yeah, then we need to redo all the calculations. So we would need to redo this calculation here for the reflection, and we would need to redo this calculation here for the absorption. And for both of them, we should get some value. So what did you get here? 0.163. 0.163, so about 16% of copper. And I will add here that our mu relative is 300. Okay, and so this is what we will insert into these new equations, or into the new values into the old equations. And I will add some section here for subtask E. Escape here all the output, that we don't see the results of the previous calculation anymore. And kappa of steel is 9.3 times 10 to the power of 6. So if we now calculate the kappa relative, it's kappa of steel divided by kappa of copper. And if I do this, if I check this quickly, F9, we get your 0.163, which perfectly makes sense. Okay, then the mu relative.
Maybe just call kappa relative iron, because
yeah,
in the
I know,
last
but
task you have to use both.
I have to use both. Okay, then I will do it in the last task because it's a very good point, but I would not like to change too much in the formulas. So because now I think I can just copy. So we are still in the magnetic near field. So I need to copy this formula, right? Show the result. Then we need to use this formula, show the result, and maybe we'll do this first. So if I run, now we get less reflection as we discussed, and we get a little more of absorption, but nothing that would really help us. So if I copy this, it's 8.75 decibel, and the other value was 0.9, let's say, or 0.86. So because of this, we also need to take into account these multiple reflections. And so if I check the corresponding slide with this correction term for the multiple reflections, which was somewhere here. Unfortunately now this simplification probably does not hold anymore. So we need to really use the original formula to do the calculation in this case, which is now really getting complicated if you just have a plain calculator, because complex exponential function, complex number here, you need to do this multiplication. In Octave, in MATLAB, of course, it's no problem. So this is the formula for the M term that I will use here in the editor. So M equals 20 times the Descartes logarithm of the absolute value of 1 minus this reflection coefficient squared multiplied with the exponential function of minus 2 times gamma times the thickness. So closing parenthesis. Okay, so before we do this, we know, okay, we need to recalculate gamma and we need to recalculate delta. And so here now we need to have the permeability, the absolute permeability of steel, and we need to use, of course, the permeability, the conductivity of steel. And mu of steel or of the iron would be, I need to do this after this, is mu 0 multiplied with mu relative. And this should be a 0, not some O, okay. So this should work, this should give us some result. So let's run everything. Yeah, and then we see, this is not making too much sense. Right? If I now calculate the total shielding attenuation, it will be negative. So this would mean our shield would amplify the signal, which is not physical because it's a passive system. Yeah, why does this happen?
Change of material.
Say again? Change of material. Yeah, I mean, we changed the material from aluminum to steel, but for the aluminum it worked, for the steel it's not working. I think there are now just too many approximations in this formula. So we are doing some small mistake here, we're doing some small mistake here, we might also do some small mistake here, and so they somehow add up that we get some total negative shielding efficiency. So if I copy this, this is minus 12 dB. And so this means that our overall shielding attenuation is, let's say, 0. Right? We calculate something negative, but it does not make sense. What we can, of course, do and try is to take our exact formulas. So we have already recalculated delta and gamma. So I would just copy the remaining terms here. The wave impedance in air should not change because it's still the same source. But the wave impedance in metal, of course, changes. We need to recalculate this one. So the wave impedance in metal, this was this formula here. And so instead of the conductivity of aluminum, we need to take the conductivity of steel. And so if I run this, and the semicolon here needs to be gone so that we see the output. So yeah, then from the exact formula we get some shielding attenuation, but it's also negligible, right? It's not very meaningful. It would not really help us. So yeah, this assumption of it's more or less 0, I think is still valid. Okay, so let me quickly once again check if we did not do any mistakes here, but I think yeah, if we quickly go back to the task, we have the same field conditions as in D, just the conductivity and the permeability changes. So if we go back to Octave and check the script here or check the formulas, so we've changed the conductivity and the permeability, and so therefore skin depth changes, propagation constant changes, and the wave impedance in metal changes. And I think we should have acknowledged all these changes. There are no remaining values from the aluminum thing, right? Okay. Okay. Excellent. So to maybe do not lose the overview, let's do a quick summary in between. So we have started with some, if I scroll up, we have started with aluminum foil, and with the aluminum foil we would like to shield a far field transmitter. We got pretty good shielding attenuation just of this very thin aluminum foil, no problem. Okay, so then we changed into a Wi-Fi transmitter, which was still far field. It got even better because higher frequency means less reflection but more absorption, so overall it was getting better. Then in task C we changed into a near field, electric near field. An electric near field meant more reflection, which helped us, but almost no attenuation anymore because skin depth is so large then in comparison with the thickness of the material. So here what only helped us is the reflection, no absorption anymore. If we change into a low impedance field, we have much less reflection. We still don't have absorption, so overall shielding attenuation is very bad. And so now the idea was, okay, if instead of aluminum foil we will use steel foil, then it's getting better. But it wasn't. So the steel, even if it has better or higher permeability, does not really help in this case because we still don't have absorption. And at this low frequencies we also won't get reflection. So what would we need to do to get some reasonable shielding attenuation? I mean, the frequency is low, it's given by our application. We could use some material with higher permeability probably, or some higher conductivity, but then usually if you increase this, you will somehow decrease this. So what is the only thing that we could do, what is remaining? The thickness. We can increase the thickness. So now let's increase the thickness and try to think about the problem. Which thickness of the metal has to be chosen to achieve a minimum shielding attenuation of 50 dB using the same field and material parameters and so on as in this task and in this task. So let's do it for aluminum, let's do it for steel. And which material would you choose if weight is important? And steel is about 3 times heavier than aluminum, or aluminum is 3 times lighter than steel. Okay, I think I don't have much space here to write, so I will maybe directly go to a new page. And we before used blue, so let's use green once again for subtask F. Okay, so this is, I think, the overall shielding attenuation. This is not only including absorption. So yeah, if let's do some kind of table. Let's say we have aluminum, and here we have the steel. And if we take a look at the reflection parameter, so for aluminum it was something like 39 dB, and for steel it was just 9 dB, let's say 8.75. So this was 39 dB, and this was let's approximate it to 9 dB, right? We could have the exact values. So now the question is, how many absorption do I need to get some overall shielding efficiency of 50 dB? And here also we want to get 50 dB. So how much do I need here? 11. And on the other side, 41. And as both of them are greater than 10, we don't need to take into account this multiple reflection term. Okay, so then we can go back to our absorption loss formula, which was this one here. And now we could rearrange this absorption formula to give us the thickness. So if I would like to calculate thickness from this, thickness in millimeter, is we take A and we divide by all the other terms. We divide by this 130.3 dB, and we divide by this square root. And I'm a bit lazy, so I won't write all the values from the square root, but that's the manipulation of this formula, right? Okay. So let's go back to Octave and so for subtask F, maybe I find the values that we had before. So for this was what we got for steel. This was what we got for the aluminum. And so our overall shielding efficiency minimum is 50. This was for iron, this was for aluminum. And so we can calculate the necessary shielding attenuation by absorption for iron is this minus this, and this should give us the 41, and the aluminum thing is this value minus this value here, and this should, right, if I try this out, F9, we get 41 and we get approximately 11. So this fits. Okay. And so now we can use this formula that the thickness in millimeter, and let's once again start with the steel case, is the necessary absorption loss for steel divided by, divided by 130.3 and divided by the square root, and inside the square root there was the frequency in megahertz, and this should still be the correct value, the mu relative of iron. And now I need to take into account Francesco's comment, because this is not yet set, and the kappa relative of aluminum. And so let's check if we find these values here somewhere. This was the kappa relative of steel. And the kappa, the mu relative of steel was is 300. And
in the square root, it's aluminum?
In the square root, it's aluminum.
Okay.
And this should, of course, be steel. And so now we need to do the same thing once again for the aluminum case. So this needs to be changed to aluminum. For aluminum, this is just 1, and I also need to change it here and there. And then
also the A.
And also this value here, exactly. So I'm not sure if we will find this here somewhere really on the top. I know that we had calculated it somewhere, but I think we can just recalculate. It was kappa of aluminum divided by kappa of the copper, and so this was the proper value that we need in this case, and this needs to go here.
Also the attenuation.
And also the attenuation, and also, of course, the result. Very good point. Okay, so this should hopefully do the job, and I will just run and maybe escape the output from what we got here before, so that we don't get confused. And there's still some m somewhere being calculated. I think it's this one here. Okay, so this tells us we would need to have 0.7 millimeters of steel or 1.6 millimeters of aluminum. So if we now say, if we go back to the task and take a look, what would you choose if weight is important and steel is about 3 times heavier than aluminum for the same thickness? If I take the steel and multiply it, or so if I take this, multiply by 3, then it's would be thicker than the aluminum. So the aluminum
1.6
is lighter, would be better in this case. Aluminum is thicker, but it's still lighter.
Yeah.
Okay. So here we would go for the aluminum. And then we can do the same thing once again in the last subtask G, and say now we want to end up with 80 dB. So I think just use the very same table here. So if we want to go to 80 dB in this case, if we want to go to 80 dB in this case, this is staying the same. Then of course we need 30 dB more here, and we also need 30 dB more here. And we just need to reinsert this into these formulas here and recalculate the thickness. So this is what I will do in the editor. I will copy all this stuff, rename it to subtask G, and I think I only need to change one value, the 50 into 80, and recalculate all this stuff here. And this is what I will do just with F9. And so our new result, there's a question?
That should be 41.
Yeah, this should be 41 dB. Right. Yeah, I said we need 30 more, and 11 plus 30 is of course 41. So very good point. But it's believe me or not, it's always the challenge of speaking and writing at the very same time. Okay, so now we get that we would, instead of this have been the old values here, so instead of 0.7 millimeters of steel, now we would need 1.2 millimeters of steel. But instead of the 1.6 or 1.7 millimeters of aluminum, we would need to have 6.3 millimeters of aluminum. And so now in this case, the steel would be favorable, or would be to choose, would be the better option. It's thinner and it's even lighter. And yeah, so this is, to summarize, let's say, this is the big advantage of this shielding theory according to Schelkunoff, that yeah, you have these, let's say, approximate but still correct enough, exact enough formulas that would allow you to do such calculations, right? We change a bit, and so this reflection term will stay constant, but here overall will change, but so we need to have more absorption, and what does it mean for the thickness of our material, for example. And so if you, and this is the nice thing of all these approximative formulas that we have set up, if you would like to do the similar calculation from this original formula here, it would be much more complicated and much more challenging, because if you would like to find the thickness from here, the thickness is in here, the thickness is in there. So how would you reformulate this equation to give you the thickness? Yeah, you would also have to take the assumption that this term at the end does not really matter, because this is negligible in comparison with the other ones, and so on and so on. Yeah, and as said, I mean, this is big advantage of Schelkunoff theory, that you have some nice handy formulas, rules of thumb formulas, to say, okay, I have this material, I have that thickness, I have this and this frequency, I have a near field and far field. What would be the overall shielding efficiency of my shield in this case?